All right, so today we'll talk about work, energy, and power. Okay. What you learn is to do work, you need energy. Okay. Power is just the rate at which you're doing work. And since you need energy to do work, power is the rate at which you're consuming energy. Okay. And so we'll see how it relates to humans. Okay. So we'll first learn these physics concepts and then apply them to our body. Okay. Again, Professor Feynman is one of top physicists, and he says, I think it's much more interesting to live not knowing than to have answers which might be wrong. So it's better not to know than to know the wrong answers. All right, so we need energy to do work. Okay. And so that's why your body does various processes. When you lift an object up, you've done work. Okay. So I need energy for doing that. You pump blood. Your heart pumps blood. It gets the blood flowing. It needs energy to do that. It's doing work. It needs energy to do that. When you breathe in, your diaphragm has gone down. You've done work. You need energy to do that. Okay, so there are all kinds of processes that need energy. Okay, so every bodily process requires energy. Physical work, when you lift an object up, when you run and stuff like that. Blood circulation, digestion, sleeping, and even thinking. Okay, when you're thinking, there are ions that are going in and out of the cell. And then you have to reset those ions, and it takes energy to do that. Okay, so the body is an energy converter. Okay, we'll come to that, what that means. Okay. With the intake of energy being food that the body uses for one of many things. Okay, conduct internal processes, do mechanical work, produce thermal energy, and store excess energy as fat. Okay, so let's do this. So how do you bring in energy? I'm sorry? Food. And so you do work with it. You produce heat with it. Okay, heat production is also one of the byproducts. So for instance, we are warm-blooded animals, and we maintain a 37 °C temperature. Okay, that's your internal body temperature. So as you lose heat, you have to produce heat to maintain that body temperature. If you produce excess heat, you sweat and get rid of it, I guess, and we'll talk about that in one of the later chapters. What if you don't produce enough of it, like in the winter? So, I'm sorry?
No, I was going to say you freeze.
So you have to, a couple of the strategies are you try to minimize blood heat loss. How do you do that? You reduce blood flow to the extremities, so you minimize blood loss. And you shiver. When you shiver, your muscles are working against each other. They're doing work. They're not doing work, and all the energy expended is turned into heat and stuff like that. Okay? But anyway, so you need energy to do work in various processes. Part of it goes into heat generation. And if you're not using all of that, then you store it for a rainy day. Okay? So those are the three things you do. Okay? All right, so all right, so here's an example of doing work. Let's say you lift this object up. Okay? If you lift this object up through a height h, this is the amount of work you've done. The mass of the object times the acceleration due to gravity times the height through which you lifted that object up. Okay? So that's how much work you've done if you lifted this object up. All right, so here's the deal. If 100 joules of work, joules is a unit of work and energy. If 100 joules of work is done on an object, so if you do 100 joules of work on this object, it gains 100 joules of energy. Okay. So if you do 100 joules of work on this object, it has gained 100 joules of energy. Okay. That energy didn't vanish. So when I lifted this object up and I did 100 joules of work, it gained 100 joules of energy. Where did that energy come from? I'm sorry? From me, very good. So I lost 100 joules of energy. Nothing was created or destroyed. So when I did work on this object, what happened? I transferred energy from me to it. Okay. All right, so that's one thing about energy. You do not create it or destroy it. You can transform it from one kind to another. What do I mean by that? Okay, what kind of energy did I have in my body? Chemical energy. And in transferring from here to there, I also transformed it from chemical energy to this is mechanical energy. Okay. All right, so energy cannot be created or destroyed. It can be transferred from one object to another. It can be transformed from one type to another. Okay. All right. So energy comes in various forms: mechanical, chemical, radiant, nuclear energy, etc. It cannot be created or destroyed. It can be transformed from one type to another, meaning chemical energy can be converted to mechanical energy. Heat energy can be converted to mechanical energy. Mechanical energy. Do you know, does anybody know an example of this? Where this happens? You do this every day. In your car, when you burn gasoline, the gasoline releases heat, and that is converted to the motion of your car. Okay? So your car is a device to convert heat to mechanical energy. Okay? All right, so we're doing that in our lives all the time. Okay? So it can transform from one form to another and transferred from one object to another. So you just saw that when you do work on an object, you're transferring energy from you to that object. Okay? Okay, so in everything we do and everything that happens in nature, energy is only transformed from one form to another and transferred from one object to another. You do not create energy or destroy energy, so the energy of the universe is constant. Okay? So here are various forms of energies, like solar, nuclear, coal is chemical energy, wind energy is kinetic energy, water at a higher location is potential energy, and so on. Okay? And everything we do, we convert energy from one form to another. Okay? So any form of energy can, in principle, be converted to any other form of energy. So heat can be converted to mechanical energy, like you do in your cars. Mechanical energy can be converted to heat. When you brake your car, when you stop your car, what happened to all the mechanical energy? It got converted to heat. Okay, just like that. All right, some are more efficient than others. So what does that mean? Okay, so for instance, when you're driving your car, you're going at 70 miles an hour, you hit the brakes, your car stopped. What happened to all of the mechanical energy? All of it got converted to heat. Okay? All right, when you burn gasoline, you've released heat. Do you guys know how much of that is converted to the motion of the car? About 20%. What happened to the other 80%? You can't, remember, you can't destroy energy. So what happened? It went, 80% went out your tailpipe. Huh? Went out at the exhaust. Okay. So for every $5 of gas you put in, you're getting $1 of motion. Oh, well, that's not even the complete story. Let me awaken you to this. It gets worse. Okay. So here's the car, and I'll keep it simple. So what's your goal when you get in your car? To get from point A to B. Okay, so when I get in my car, I'm not 200 pounds, but we'll say I'm 200 pounds. My goal is to transport 200 pounds from here to there, right? I get into this 4,000 pound car and get from here to there. Well, what did this 4,000 pound do? It only had 20% efficiency, okay? So if I put in $5 worth of gas, I got $1 worth of motion. Okay. Well, actually, I'm going to make it even. I put in $100 worth of gas. I got $20 worth of motion. Yeah. But my goal really was to transport this 200 pounds. And this was 4,000 pounds. To transport 200 pounds, I transported 4,000 pounds. Really, this is 10% of that is 400 pounds. 200 pounds is 5%. So really, I got 5% of that. 10% of that is $2, 5% is $1. So to achieve a goal of $1, I spent $100. Think about that when you get in your car next time. Okay? All right. So the point is, any form of energy can be converted to any other form. Some forms are more efficient. Some conversions are more efficient than others. So mechanical energy can be converted all into heat. Heat to mechanical energy is less efficient. So heat to mechanical energy conversion is only about 20 to 40% efficient. So it's, okay, in your car, it's about 20% efficient. And in a coal power plant, it's about 40% efficient. So in this example, this is a swinging pendulum. This has potential energy. As it swings down, that gets converted to kinetic energy, back to potential energy, and it'll go back and forth. Okay. So potential to kinetic energy, this was 100%, 100%, 100%, 100%. Okay, so as long as there is no air resistance, this will keep going forever. Okay. So this is the formula for potential energy. Okay. And this is the formula for kinetic energy. All right, so everything we do from an energy perspective, we're just converting energy from one form to another, or we're transferring it, and we're transferring it from one object to another. Okay, so here are various devices. So from the sun, you get electromagnetic energy, and solar cells can convert it into electrical energy. Okay. Light bulbs can convert electrical energy back to electromagnetic radiation. Okay. You can take electromagnetic energy, and plants can convert it into chemical energy for us. Okay. You can convert chemical energy via oxidation back to electromagnetic energy. Mechanical energy, you can so you can take chemical energy like in gasoline, and in a car, which is a heat engine, convert that to mechanical energy. Okay? Mechanical energy can be, via friction, can be converted to heat and stuff like that. Okay? So mechanical energy via friction can be converted to heat. Electromagnetic energy, radiant energy via heat engines can also be converted to mechanical energy. Okay, so here are all these devices that we use in our lives that show you how to convert one form of energy to another form of energy. Okay? All right, so here's the energy flow roughly in our lives. So we get all of our energy, essentially all of energy from the sun. Plants are the first devices that capture this energy, and now we have solar cells and stuff like that, but most of the energy is captured by this plants. They convert this radiant energy to chemical energy. We eat plants, so the chemical energy is refined, if you will, but it stays as chemical energy, and when you ride your bike, that chemical energy is converted to mechanical energy, and that mechanical energy is eventually converted to heat, which is radiated back out. Okay? So that shows you the energy flow. Okay, now let's let's see how you calculate work done. Okay, so let's say you have an object, you apply a force, and then you push it through a distance d. If the force is constant throughout the push, the work done is just the product of the force and the distance. Okay. Force is measured in newtons, distance is measured in meters, and this Newton meter is called a joule in honor of Mr. Joule. Okay. So the unit of work is joule. Yeah. Now we learned that you need energy to do work, and so energy and work have the same units. Okay. Energy and work are measured in units of joules. All right, so this is how you calculate work. If the force and the distance traveled are parallel to each other, work is just force times distance. What if you're applying a force like that and the object moves in this direction? Okay, when there's an angle between them, this is how you calculate the work done. The work done is force times distance times cosine of the angle between the two, between the force vector and the displacement vector. Okay, now this guy, this fellow here, cosine theta, he can be positive, he can be 0, or he can be negative. Okay. Depending on the angle, depending on the value of the angle. If the angle is between 0, if the angle is acute, then this is positive. If the angle is 90 degrees, this is 0. And if the angle is obtuse, between 90 and 180 degrees, this is negative. Okay. So work done by the force can be positive, negative, or 0, depending on whether the angle theta is acute. Acute meaning less than 90. Okay. So then work is positive. When the angle is 90 degrees, work done is 0. And when the angle is between 180 degrees and 90 degrees, then the work done is negative. Okay. So you can do positive work, negative work, or 0 work. Okay. When I do positive work on an object, I increase its energy. When I do negative work on an object, I decrease its energy. Okay. So here are examples. Okay. So in this picture, okay, this guy is lifting this suitcase. He's applied a force on the suitcase because gravity is pulling down, but he's not moving, so he's doing 0 work. Okay. So for instance, I can push on the wall. I'm not moving the wall. I am applying a force. I'm getting tired, but I'm doing zero work. Okay. In this case, again, he's lifting the suitcase and he's transporting the suitcase in this direction. The force and distance traveled are perpendicular to each other. Theta is 90 degrees, so he's done zero work. In this case, so here, when he's lifting the suitcase up the stairs, there's the force he's applying, there's the displacement, there's the angle theta, and he's done positive work. In this case, so let's say this suitcase is being lowered, the force applied is in this direction, there's the displacement. The angle between the two is 180 degrees. Cosine 180 is -1. Okay? So the work done will be negative. Okay? So for instance, you do this all the time. So let's say you're driving at 70 miles per hour, and then you apply brakes, your car is moving forward, and the braking force is in the opposite direction, okay? And so you're doing negative work when you apply brakes. And when you do negative work on an object, you reduce its energy, and you're stopping the car, okay? So you do that all the time. All right, so here's how you calculate the work done, and the work done can be positive, negative, or zero. Okay. Now let's talk about power. Power is work done divided by the time it took to do the work. Okay. So if you do a certain amount of work in less time, that means your power is greater. Power is also, to do work you need energy divided by time. So power is also the rate at which you're consuming energy. Okay. Now the units for power are work and energy are measured in joules in SI units, and the SI unit for time is second, so joule over second, and this is called a watt in honor of Mr. Watt. Okay. So that's the unit of power. Okay. Now a horse can work at the rate of 746 watts, 750 watts for a whole day. If you want a horse to work for eight hours, it can work at the rate of 750 watts. Humans, on the other hand, if you want to work for 8 hours, you can work at the rate of a tenth of a horsepower. Okay? So in a field, a horse can do the work of 10 people. Yeah, so that's why we used horses. That's why we used animals. All right, so for instance, if you're climbing the stairs, the work you've done in climbing this height h is m, your mass, times g times h. Okay. Now if you run up the stairs, this time is smaller and your power is greater. Okay. All right, so in this problem, this nurse, there's the center of mass of the nurse and this baby. When the nurse lifts the baby up, see the center of mass has risen by this height h, and so the amount of work done is m, the mass that is lifted, g times h. Okay, so when she lifted the baby up, she lifted herself, her center of mass, she raised her center of mass, and the baby, the combined center of mass rose. So this is the combined mass. Okay. And so this problem goes through there, just calculates that. So this is the combined mass, g is the acceleration due to gravity, and the baby and the center of mass rose half a meter. Half a meter is about 2 feet. Okay. And so about 370 joules of work was done in this case. Okay, if you wanted to calculate just how much work was done on the baby, you would put just the mass of the baby. Okay? All right, so this is our source of energy. Okay? So many of the most common energy sources are chemical in nature. Food being one time of food is but one type of chemical energy stored. Gasoline and others, we use those sources of energy as well. Okay. The energy content of food is given in units of kilocalories. Okay. So we'll comment on that in a second. Excuse me. Can you lift your bottle up? Okay. So if you take a cap full of that water, that's about 1 gram of water. The heat needed, okay, so to raise the temperature by 1 degree Celsius, 1 degree Celsius is about 2 degree Fahrenheit. To warm that much water by 1 degree Celsius, you need 1 calorie of heat. Okay, so that's the definition of a calorie. The food calorie that you talk about, you see when you see on a yogurt, it says 80 calories. A food calorie is a big calorie, is really 1,000 of these little calories. Okay, that is a kilocalorie. That's a food calorie. Okay, so you just need to be aware of that. A kilocalorie is 4,186 joules. All right, so this lists various energy content of various foods. So on the average, carbohydrates have 4.1 kilocalories per gram, or 4.1 food calories per gram. Okay, that's the energy content of carbohydrates. Average proteins have the same. Fat has twice the content, energy content. Okay? And you know, that's why when you store energy, you want to store it as fat, because then you don't have as much volume to store. Okay? Remember, if you store excess energy, you have to carry it around, and so you want to store it as the highest energy density. That makes more sense, right? I mean, if you have to, you don't want to store it as, if you store it as proteins, what would happen? To store the same amount of energy, you have to carry twice the weight. Okay? So you don't want to store it that way. Okay. So if an animal consumes more food than it's needed to do work or keep warm, it will convert the excess energy to fat. It stores it in the bank. Okay? All right, so what happens if you eat excess calories, and what do you need to do to get rid of it? Okay, so if a person who normally requires 3,000 kilocalories of food, so 3,000 food calories per day, instead consumes 4,000 calories per day, they gain weight. Okay, so what do you have to do to get rid of the excess energy? Okay, so you're eating 1,000 extra calories per day. What would you have to do to get rid of those excess calories? Exercise. So this table shows you various activities that you can do. Okay, so cycling, this is a normal pace, and this is not very fast. This is fast. Okay, so a normal pace cycling, this is, you're using 5.7 kilocalories per minute. Okay, so if you want to get rid of 1,000 calories, 5.7 calories per minute. I mean, when I say calories, I'm saying food calories. Okay? And if you divide that by that, you get 175 minutes. So you have to bicycle for 3 hours to get rid of that extra 1,000 calories. Yep. go get a cheeseburger and and get on the bike for 3 hours. Well, so again, we've talked about various forms of energies. So kinetic energy is kinetic energy is energy in motion, and that's the formula is 1/2 mv squared. Thermal energy is heat energy. We'll talk about that more in one of the next chapters. Potential energy is, here is gravitational potential energy. It's called potential energy because you can release it anytime you want it, okay? So that's what we do in a dam. When we store water behind a dam, we've stored potential energy. Well, we've stored water as well, if you want for agriculture later, but you can also produce electricity whenever you want, okay? Light is electromagnetic energy, and energy content of mass, Einstein gave us this formula, mc squared. You guys probably have seen this formula. What this equation tells you is the energy content in mass, except that it's very hard to convert mass to energy. Okay, that's what a nuclear power plant will do. And this problem just shows you how much energy content there is. Okay, c is the speed of light. There is the speed of light. Again, can you hold up your bottle again? Okay, so you fill that with water, just the cap. If you could convert all of that to energy, this is, so there's 1 gram, that's in kilograms, that's how much energy you would get. And so there's 2,000 kilocalories. You could feed, that's the conversion to joules. So this divided by that divided by that, you could feed 10 million people for a day. All right, did you guys see that? You take 1 gram of water. If you could convert all of that to energy, you could feed 10 million people for a day. Of course, it's hard to do. Okay? All right. So that just, the whole point was to show you how much energy content there is in mass. Okay? So to give you another idea, do you guys know how old our sun is? How long has the sun been around? Anybody? Okay, it's been around for 5 billion years. Okay? And it's got another 5 billion years left, so it's gone through half its life. Okay? So the sun at the center, it's doing fusion reaction, and it's converting some of its mass into energy, and that's how we get energy. Okay? So what the sun does is takes 4 protons, converts that to helium. Okay? And this guy, so this is helium, and mass of helium, this is protons, mass of protons, so 4 protons. The mass of 4 protons is greater than mass of 4 helium. So it took this guy and made something that weighs less. It took 4 protons, fused it together, and made helium, which weighs less. So what happened to the missing mass? That got converted to electromagnetic radiation eventually, and that came to us. Okay, so that's how the sun converts energy via fusion reaction. All right. So the sun will live 10 billion years. Okay, that's the lifespan of the sun. So over its lifespan, I'm just giving you rough numbers. If it started out 100 pounds, if the sun started off as 100 pounds, it will end up about 98 pounds. So over 10 billion years, it'll lose about 2% of its mass. So that's how hard it is to convert mass into energy. Okay? So that this problem is just, as an illustration. All right, here's something that happens every day. So for instance, you can convert potential energy to kinetic energy. Okay, so you can slide down a mountain, and if that potential energy gets converted to kinetic energy. Okay, so if you slide down this mountain and if there's no friction, what friction does is friction converts mechanical energy to heat, and that's hard to keep track of. So we'll say if there's no friction, the question is how fast will you be going down that hill. Okay, so you started off as potential energy at the top, which is mgh. H is the height of the mountain, and at the bottom it all gets converted to kinetic energy. All right, the mass cancels. What that means is no matter how heavy the sled is, they'll all be going at the same speed. Okay, and the speed will be. So if you work this out, it works out to that. 2g is the acceleration due to gravity, and h is the height. So if you came down a mountain that's about 1.5 football field length, 100 meters is about 1.5 football field length. Well, 1 1/3 football field length. Okay, so imagine a mountain that high. If you slid down that mountain, you'd be going at 44 meters per second, which is 100 miles an hour. Okay, you'll be going fast. All right, so let's say you're climbing up a flight of stairs. So that is the height you climbed. The amount of work you did was your mass times the acceleration due to gravity times the height you climbed. That's how much work you did. Now power, so to do work you need energy. Okay. Power is how fast you did that work. You consume that much energy divided by the time. Okay. So let's say, so there's the mass of the person, there's g, there's the height. 2 meters is roughly this height from the ground to there. That's 2 meters. Okay. And floor is about 4 meters, 4 or 5 meters. So one flight of stairs is about 2 meters. Okay. So if you climb that flight in 2 seconds, you've done 588 joules of work, or 500 and roughly 600 watts of work. 600 watts of work is, if you divide that, that's 1 horsepower. Okay, 1 horsepower times that. So that's 0.8 horsepower. Okay. So if you run up this flight of stairs, you run it up the flight of stairs in 2 seconds, you worked at 0.8 horsepower. Okay. Remember we said if you wanted to work one whole day, you wanted to do 8 hours worth of work. At what rate can you work? I'm sorry? Very good. 0.1 horsepower. You're stressing yourself here. Okay? All right. So people with heart problems are warned that climbing stairs is one of the most stressful acts that they can perform. Okay? Now, it said that even top conditioned athletes can work at about 1/3 of a horsepower for about 30 minutes. This is top conditioned athletes. Okay. All right. Now, this part shows you if you leisurely climb up the stairs, you take 7 seconds. That's 0.2 horsepower. Okay. All right, now we'll talk about efficiency. Okay. Okay, so whenever you, let's say I lift this object up and I did 100 joules of work. In my body, just like in your car was 20% efficient. Our body is roughly about 20% efficient, depending on what you do. If you cycle, you're 20% efficient. So for 100 joules of energy spent, you only got 20 joules of what you were intending to do. Okay, so when you're cycling and you spent 100 joules of chemical energy, you got 20 joules in cycling. What happened to the other 80 joules? Heat in the body. Okay, it was wasted energy. So your efficiency was 20 divided by 100. What you got out of it divided by what you used. Okay. All right. So efficiency is work or energy out, useful energy out, or use and work or energy input. Okay. So in this case, it would be 20% efficiency. You can also calculate efficiency by power out divided by power in. Okay. So what happens to wasted food energy in a human? It goes mostly to thermal energy. Okay. And so you're using some of the thermal energy to maintain a constant body temperature. But if the thermal energy produced by the body when doing physical work is more than that is needed to keep warm, then that must be dissipated. And as we said, we sweat to dissipate the excess heat. Okay, and we'll talk about that in one of the next chapters. All right, so here is the efficiency of the body. When you're cycling, it's 20%. Swimming on the surface, you're only 2% efficient. Swimming underwater, you're 4%. Shoveling, it's 3% efficiency. Okay. Why does our efficiency vary so much? Okay, so we'll learn about that. We'll talk about that in a second. Okay. One. The more muscles, so the answer is the more muscles you use to do something, the less efficient you are. Okay, so we might as well talk. Okay, a single muscle is about 25% efficient. So if you used a single muscle to do a task, you'd be 25% efficient. So that's the upper limit. Okay? The body can never be more than 20% efficient. Leg muscles are the largest in the body. Hence, cycling and climbing stairs. So when you're cycling and climbing, you're mostly using that one muscle. Okay? A relatively efficient process. Shoveling uses arms, shoulders, leg, and back muscles. A lot of different muscles in different areas. And so your efficiency goes down because more often than not, those muscles are working against each other. Okay. So what's the point of a coach? A coach is telling you how to be most efficient. So to do a process, use the least number of muscles and so on. Okay. All right. Okay. Okay, every bodily process requires energy, physical work, blood circulation, digestion, and so on. Okay. So our body efficiency ranges from 2 to 20%. Okay. And again, you saw that swimming on the surface is 2%, swimming underwater is 4%. That's why you see that when in races, when a swimmer jumps into the pool, they want to stay underwater as long as possible. And that's about a minute before they have to come back up to breathe. Okay. And so on. That's why all fish swim underwater and not on the surface. Okay. So the more muscles you use to produce useful work, the less efficient the body is. Okay. Many organs consume energy and do no work. You'll see, let's say a body secretes enzymes and stuff like that. It's not doing any work, but it's consuming energy. Okay. Well-trained athletes are very efficient. Two individuals performing the same physical activity have different efficiencies. Okay. The person who has the fewest muscles exerting forces in opposition to one another will have the greatest efficiency. Okay, and that's what your training is about. So the generally low efficiency of the body means that significant amounts of heat is generated. The portion not needed to maintain body temperature must dissipate into the environment. Okay? So here is we'll talk about this in one of the next chapters. Okay, the air conditioning here is removing heat that we are generating. Okay. Let's say we have another 20 people walk in here. The room will suddenly get warm, right? You got to go out there and crank up the air conditioning. But your body is amazing. You're a 100-watt bulb right now. What that means is you're generating 100 joules of energy per second, and your body is getting rid of it. Okay? Every second, your body is getting rid of 100 joules. Now, let's say you go for a run. Now you become like a 1,200-watt bulb. Your air conditioning has to crank up by a factor of 12. It's got to work 12 times harder. And it does it, just like that. You try and crank up this air conditioner by 50%. You know? Okay, so anyway. So metabolic rate. The rate of conversion of food energy to some other form of energy is called a metabolic rate. The total energy conversion rate of a person at rest is called the basal metabolic rate. Okay, so your basal metabolic rate is about 100 watts. Okay, you're using 100 joules of energy per second. Okay. So here is the rate of energy consumption of various parts. So this is a resting 65 kg male. 1 kg is about 2.2 pounds. So 65 times 2 is 130 plus 13. This is a 145-pound person. Okay. Their basal metabolic rate is about 85 watts. Like I said, 100 watts. Okay. What this shows you is how much energy is used by various organs. So liver and spleen use about 30% of your energy. That's what it says. Your brain uses 20% of your energy. Okay. Your heart, that has been working since the day you were born, and it'll work till the last day, so it's a lifetime warranty. It's using 7% of your energy. Okay. Okay, the human brain we all have about 686 billion neurons. Yeah. It's the most complex energy-consuming brain on the planet. Approximately 6 calories, so 6 physics kilocalories, but 6 food calories per day are required to sustain 1 billion neurons. You have 100 billion neurons. Okay, so to run your brain a day, you need 500 calories. Okay, so if you're consuming 2,500 calories a day, 500 of those go for your brain. Okay. Per day. Okay, so here's an interesting fact. If one ate raw food, you would need to eat 9 hours each day to supply enough energy to maintain a healthy human. Okay. Cooked food is partially digested and provides the body on the average 3 times the energy per pound. Okay, so if food was uncooked, you would have to eat 3 pounds versus 1 pound of cooked food. So by cooking food, you increase the energy density of the food. Okay. So the invention of cooking 1.5 million years ago, has allowed the human brain to evolve to its present degree of complexity. Okay, so that's the theory. See, no other primate cooks, that's why their brains didn't grow. Had they learned to cook, chimpanzees could be as smart as us. Yeah. Or maybe if they learned to cook better, they could. Okay. The basal metabolic rate is related to thyroid activity. Okay. Also, basal metabolic rate is related to the mass of the person. Larger people have greater BMR. You know, they have more mass, and they have to consume more energy. Energy consumption is directly proportional to oxygen consumption. So that's an easy way to measure how much energy is being consumed. Okay, you just measure how much oxygen you're consuming. And we'll talk about that in a little detail. Approximately 4.9 kilocalories of heat energy are produced for each liter of oxygen consumed. Okay, so you want to, so we'll talk about that. Yeah. So the digestive process is quite effective in metabolizing food. Only about 5% of the caloric value of food is excreted in feces and urine. Okay, so yeah. So let's say you take in food, 95% is absorbed by the body, and only 5% is eliminated. Okay? So for every $100 you eat, only 5% of that nutrition value is thrown out there. Okay? And why do we throw out the 5%? Why not take 100% of it? Are you walking around throwing $5 out of your pocket every time? No. So it probably costs the body more than it's worth getting. Okay, so for instance, if you see a penny on the road, you might not pick it up because it's not worth your time. Okay? It costs you more. During rest, most of the energy consumption of the body ends up as thermal energy. Okay. Work done by the heart on the blood is eventually converted to thermal energy. Okay. All right. What this problem does is it shows you how much. So excess energy. So if I eat more than my body needs per day, what happens to the excess energy? I store it as fat for a rainy day. This problem shows you how much fat I would store. Okay. And again, you just have to. This is just okay. So if you're consuming 2,500 calories, and you're just, let's say I'm consuming 2,500 calories, and I sit on the couch all day long. Yeah. So if I'm sitting on the couch all day long, this is my metabolic rate, 1.22 kilocalories per day. And this is for probably a standard person. Yeah. So this is my basal metabolic rate. What this shows you is energy consumed per day is power times time. Okay, so this is my basal metabolic rate. So that's how much energy I would consume, 1,800 calories per day. Okay, that's what that shows. But I ate 2,500 calories. So if I eat 700 excess calories a day, how many grams of fat is that? Okay, so that's the problem. So 700 excess calories a day, and so this is 700 calories. So 1 gram of fat has 9.3 calories. So this divided by that, 80 grams of fat. So can you hold up your drink? So if I eat 700 excess calories a day, a third of that can is 80 grams. And that's what that problem said. Okay. Okay, so here's an important number. You saw that 4.9 kilocalories of energy is produced for every liter of oxygen consumed. Okay, now we'll talk about what do we mean by oxygen consumed. Okay. So the average respiratory rate of a person is 12 breaths of half a liter each minute. So each minute you're taking 12 breaths, and each time you take a breath, you're breathing in half a liter of air. So you're breathing in 6 liters of air per minute. Okay? And in 1 hour, there's 60 minutes, so 60 times 6. So 360 liters of air per hour. You're breathing in 360 liters of air per hour. But air is not all oxygen, okay? Air is 20% oxygen, so 20% of that, 10% of that is 36, 20% is 72 liters. So you're breathing in 72 liters of oxygen per hour. Well, all the oxygen you breathe in, you're not absorbing. Okay? Only 30% of that oxygen you're taking into your body. Okay? And 30% of that is 20 liters. Okay? 28% of that is, you just multiply that, 0.28 times that gives you that. So really, you're consuming 20 liters of oxygen per hour. Okay? And this makes sense. For each liter of oxygen you consume, you're producing 4.95 kilocalories, and so 20 times that is 100 kilocalories. Okay? Yeah. So only 28% of the oxygen that you breathe in, you're absorbing. The other 72% is exhaled. And so that's why mouth-to-mouth resuscitation, CPR, blowing on charcoal, and so on work, because there's still plenty of oxygen when you breathe out. Yep. Okay, this problem just goes through the following. Oxygen consumption during cycling. Okay, so your oxygen consumption is roughly tells you your energy consumption. Okay, so oxygen consumption during cycling and oxygen consumption during sleeping. Okay, so when you're cycling, you're working about 8 times harder. Your energy consumption is 8 times higher than when you're sleeping. That's what that problem shows you. Anaerobic and aerobic phases. Okay. So this happens, the anaerobic phases happens when, let's say, you're in distress, you want to run away from a lion chasing you or whatever, you know. So what the body does. You know. And this is aerobic phases when you're cycling or going for a run and stuff like that. Okay. In the anaerobic phase, humans and other animals can work for short periods of time at much higher rates than can be maintained. This ability is useful in emergencies. Okay. So what does the body do during this phase? To do this, the body rapidly oxidizes available blood sugar. Okay. So to get that extra boost of energy, whatever blood sugar is there in the blood, you rapidly oxidize this with oxygen already present in the body. You're not wasting, you're not bringing in any more oxygen. Whatever is there, all the resources that are there, you're using up. Okay? And makes the resultant energy available to vital organs and skeletal muscles. The heart rate increases to circulate blood substances more rapidly to areas where they're needed. Blood flow patterns are altered to send blood to organs active in stress response. So all this is happening very fast, and all this can only last about 1 minute. Okay? So there are so many things happening. The spleen contracts to put stored blood into general circulation. The spleen stores blood, so that'll also supply the extra blood, which has oxygen and glucose content. The liver transforms large amounts of stored glycogen into glucose. All these things are happening in under 1 minute. Why? So you can get away, run away from that lion. Yeah. So the liver transforms large amounts of glycogen into glucose and releases it into the blood. All these actions utilize oxygen already in the body. So even the anaerobic process is using the oxygen, but it's using existing oxygen. Okay? And you're not breathing in. You don't have the time to bring in more oxygen. This stage called the anaerobic phase. The higher power output cannot last but more than about a minute. Okay? The aerobic phase, you start breathing, the body quickly becomes oxygen deficient during the anaerobic phase and requires oxygen from lungs to maintain its activity. It thus enters a new stage called the aerobic phase. So now you have to work long-term. A series of actions are initiated that make possible the long-term production of energy. This includes sweat production, because now you're working harder, you're producing more heat than is needed. You got to get rid of the excess heat fast. You produce sweat. Rapid breathing, you're using energy at a large rate, so you need to bring in more oxygen. And dilation of air passageways. Why did your air passageways dilate? To let the air in. So we learned that in the first chapter, we learned that to make a fluid flow, you have to have pressure difference, and the flow rate was given by this equation. You don't have to remember this equation. To increase flow rate, you can increase the pressure difference. Okay, pi r to the power 4. R is the radius of this tube. 8 eta is the viscosity. So the best way to increase flow rate is to increase the radius. You saw in one of the problems, you increase the radius by 50% and you increase the flow rate by 500%. Okay? You want to bring in more air, just dilate your breathing passages. Okay? And so on. When you eat a meal, your blood flow to your digestive system increases by a factor of 5, and that's how it's done. Okay. All right, so we talked about energy. We bring in energy via food. There's 3 things we do with it. You either work, you use it to produce thermal energy. Well, thermal energy is also produced as a side product of many things. Or if you brought in excess, you store the excess for a rainy day. Okay? And why do we store it in as fat? Why do you store the excess energy as fat? I'm sorry? Pound for pound, you can store more energy in fat. Okay? So in 1 pound, you can store twice the energy as in 1 pound of protein. Okay? So that's why we store it. So the energy density is higher. Okay? The last 2 slides, so I just want to show you. Okay, so you guys saw that the liver and the spleen use 27% of your energy. Okay, so why is it that they need so much energy? And this is not in your book, but anyway, so this goes through all the processes, the energy intensive processes that the liver and the spleen do, and the reasons they need energy. So liver, for instance, the liver processes nutrients absorbed from the digestive tract. It performs gluconeogenesis, that is producing glucose from non-carbohydrate sources. Carbohydrate sources to glucose is easy. You just chop up the large molecules. Okay? So glycogenesis, storing glucose as glycogen. Okay, when you and glycogenolysis, breaking down glycogen into glucose. Remember, you have to break down glycogen to glucose. Okay. These processes require a constant supply of ATP, the energy currency of the cell. So liver and spleen consume 27% of your energy, and that shows you why it's done. Okay, those two slides. All right, you guys log in. I'll turn on the quiz, and the exam for this chapter will be due next Wednesday. Okay. By the way, is the pace okay? Am I going too fast in the lecture? Okay. Everybody's good with it? All right. You guys understanding the stuff?